many of those things which like Professor Sinha talked about. And like me, she started from theoretical physics background, but lights and entanglement, all those things are too good for a theorist to ignore. So very quickly she got into it. Tremendous contribution to theory of fractional revival. Its connection with classical thing, you saw the connection of classical and quantum in Professor Sinha's talk. And so similarly to fractional revival, also there is a connection with classical time series analysis, then tomography, and so I request Professor Lakshmi to talk about her work.
Thank you very much. I have been part of this QIQT since 2017, and I have actively participated in the QIQT series. I have learned a lot from the QIQT series. So both from the student participation and from the speakers who have been involved in this series. And I always keep waiting for the next edition of QIQT. I should say that it's one of the very well organized, I don't even know if I should call it conference or workshop or tutorial sessions, because I've seen a mix of everything in QIQT. I think there's some extraneous noise. Yeah, now that's gone. So I hope you can hear me clearly. Can you hear me?
Yes, ma'am.
Okay, good. Because I myself have some network problems here. So I'm going to share screen and let's see where we go. So can you see the screen?
Yes, we can.
Just a moment. So this is the full screen mode, I guess. So the title of my talk is Reading an Optical Tomogram. As Professor Prashant Panigrahi mentioned, I have been interested in tomography for a while now. And the point is this: what you get from experiments, the experimental data, can be binned in the form of histograms. In the context of optics, this set of histograms is called an optical tomogram. Now, from the tomogram, you will try to reconstruct the state of light if you're talking about optics. This becomes an arduous task for a very important reason that as you increase the number of subsystems which are interacting, for instance, if you have a lot of atoms interacting with the radiation field, then you're really dealing with many systems, and getting the state, reconstructing the state of the system from your experimental data, which is the tomogram, becomes a rather difficult proposition. So of course, once you reconstruct the state, or equivalently the density matrix, then you can calculate very many properties of the state. You can find out its squeezing properties, the extent of entanglement between various subsystems in your full system. And if the system is evolving in time, you can worry about the properties, the way they change during dynamical evolution and so on. But reconstruction is an arduous task. And of late, we deal with arrays of things. You see, be they qubits or be they radiation fields interacting with atoms as in a hybrid quantum platform, you find that there are too many subsystems, and recreating the state is not an easy matter. So the whole thing comes under my own approach, comes under the canopy called Understanding the Quantum Classical Divide. You see some effects in quantum physics, such as squeezing, as you know, have no classical analogs. They stem from the Heisenberg uncertainty principle, which is simply not there in classical physics. But then there are some effects, such as the wave packet revival phenomena in quantum physics. And there are parallels. There are classical parallels, for example, in the Talbot effect. Then there are some effects such as entanglement, quantum entanglement. But you will find that in optics, people talk of classical entanglement. What they mean is you can worry about entanglement by using electromagnetic waves and by, without invoking photons. So this is classical entanglement in the context of optics. What you will do is you will worry about the entanglement between the polarization of the electromagnetic wave with its orbital angular momentum modes. So as I have listed out here, there are certain effects in quantum physics which have no classical analogs. There are certain effects which have classical parallels. And there are certain effects which you can study using some kind of classical platforms. Now, you need to understand what is this quantum classical divide? I mean, how narrow is this divide? What is genuinely quantum mechanical, and so on and so forth. So if you want to investigate the classical quantum links, the overlap between classical and quantum physics, the differences and so on, I find optics to be an ideal platform. And the way to look at tomograms is really to understand that there is an underlying mathematics of probability theory. So as you know, even in classical settings, probability theory is there. You don't have to invoke quantum physics to understand probabilities. As far as quantum mechanics is concerned, it is inherently probabilistic. Now, if you look at different states of light in optics, they are distinguished by distributions, such as the Wigner function. Now, the Wigner function is what you will recreate from the tomogram. But that is a quasi-probabilistic function, because if you plot it as a function of x and p, and you should not confuse, I'm talking to the students now, you should not confuse x and p with position and momentum, but rather with the field quadratures, the electric and magnetic field quadratures. Now, if you plot w of xp as a function of x and p, it will be negative for many states of light in some regions of this xp plane. Whereas I have stated here, x and p are the field quadratures. The bold phase x and p are the operators. So you see, the non-classicality shows up because of negativeness of the Wigner function, and the blue-blooded good probability distribution is positive. And therefore, the negativeness is what makes it a quasi-probabilistic distribution. But in contrast to the Wigner function, which is reconstructed from the tomogram itself is a good probability distribution. It's a collection of probability distributions. It is not quasi-probabilistic. So the idea is this. You start from the tomogram, which is what you get from experiments. It's a collection of probability distributions. You attempt to understand different states of light just from the tomogram. And you should see the differences between the classical and the quantum approach. You should see the limitations in using a set of probability distributions instead of worrying about the quasi-probability distributions. This is an approach, which is what I will like to worry about. The approach, as I have already said, has advantages because you can avoid reconstructing the state as far as possible. So the question is, what is a tomogram? So data available from measurements is binned as histograms. And if the measurements pertain to light, they provide for you the optical tomogram. Essentially, what you do when you look at a tomogram is it's like a medical scan or imaging. So at different angles, and I will tell you what these angles are, an output image is obtained. Think of a medical scan. Now, each image is a slice of the tomogram, and therefore each image carries partial information about the object. Now, the full state is to be reconstructed from the tomogram. That means from the set of all slices or images. Now, therefore, you can have classical tomograms. You could be working with classical optics, treating light as an electromagnetic wave. Or you could talk about quantum tomograms. That is where you think of light as photons. There are a whole lot of papers by Manco, V.I. Manco and his collaborators on classical tomography, quantum tomography, and so on. Certainly a very detailed formalism has been given. And as I said, the underlying thing is probability theory. Now, when you look at slices, even in a medical scan, in practice, only a finite number of slices can be obtained. Now, in principle, we need an infinite number of slices to reconstruct the object. So the kind of questions you will ask is, what is the optimal number of slices needed to reconstruct the object? This is the area of state reconstruction from the tomogram. Now, of course, the number of slices needed depends on the system considered. But then you will ask, can there be any favored set of slices? Now, for instance, could these slices correspond to canonically conjugate variables? If you're talking of something mechanical, such as position and momentum. Now, if you're talking of something in optics, it would be the field quadratures, X and P, as I have already mentioned. So the question is, can you avoid detailed reconstruction of the object and infer its properties from a finite set of images? That's what you mean by taking a tomographic approach. Now, we do that in a medical scan, where even qualitative features and changes compared to a reference scan are important. So here is a flow chart. You start with the experimental data, top left. And then you bin it and get the quadrature histogram, from which that set of histograms is the optical tomogram. Now, if you want to reconstruct the Wigner function, you could do that, but that is a statistical procedure. It's inherently error prone, and the problems are going to increase the more the number of subsystems in your system. Instead, you can read off as much information as possible directly from the tomogram about the state of light that you're thinking about. So what is it that I want to really read from a tomogram? They could be non-classical effects. So I told you that the quantum analog of the Talbot effect is the revivals. So what I mean by that is, if you pass a quantum wave packet of light through a nonlinear medium, nonlinear atomic medium, for instance, the initial wave packet returns to its original form, apart from an overall phase, at integer multiples of a revival time called T-rev. This is the, and then there is the analog of the fractional Talbot effect. That means at half the Talbot distance, if you are talking Talbot effect, but here at half the revival time, so the distance in the Talbot case is replaced by time here, you have the two sub-packet fractional revival. That means two bonsai versions of the original wave packet. Now at a third of the revival time, you will see three sub-packets, each of them looking like copies of the original wave packet, but smaller versions. So at time T-rev by Q, you expect Q clones of the original. By smaller, I mean that the amplitudes are less than the original. These are quantum copies. There's an extensive and rather comprehensive article by Robinett in Physics Reports, even in 2004, on revivals. Then there is this nice pedagogical article called Quantum Carpets, Carpets of Light, by Berry and collaborators in Physics World. This could be a good starting point to study revivals. The reason why wave packet revivals and fractional revivals appear is because of interference between the basis states constituting the quantum wave packet. And of course, you know that if you look at the other non-classical effects, squeezing and higher order squeezing, it's because of the uncertainty principle. And you do know that quantum entanglement requires at least 2 subsystems, and the interaction could create entanglement. So how many of these can be mimicked by classical physics? Will tomograms tell the difference between classical and quantum physics? More work needs to be done in this area, but I will recount for you what the state is now. So before we worry about the experiments to test revivals, entanglement, etc., you should understand, if you, again, I'm addressing the students here, if you do not know the analogy between optics and the quantum harmonic oscillator, if you look at the oscillator and if you set m, omega, h cross, everything to 1, the Hamiltonian is essentially x squared plus p squared. And if you compare it with the electromagnetic field, the field energy density, if you set mu naught and epsilon naught to 1, it is E squared plus P squared. So you can take the entire mathematics of the oscillator, but use it in the context of optics, because if you quantize the electromagnetic field, you're going to get photons, except that you will reinterpret the ladder operators of optics, A as the photon destruction operator and A dagger as the photon creation operator. And A dagger A is the photon number operator. And this ket n that you see there is the n photon state. So by going from a single simple harmonic oscillator to the theory of the electromagnetic field, you have moved to multi-particle creation. You see, in a simple harmonic oscillator, your ket n will be the nth level of a single oscillator. Whereas here you're talking about the n photon state. So you have moved using the same mathematics to many particle creation and destruction. So this A plus A dagger by root 2 is X and A minus A dagger by root 2I is P. But these are now the field quadrature operators. I will have my Hamiltonian as X squared plus P squared, but these are the electromagnetic field, or the electric field and the magnetic field. You can work with different states of light. As I said, when you do tomography, you need a reference scan. Even in a medical scan, you need a reference scan. The doctors will tell you, you please produce the last scan that you took, and then compare to that, what are the changes. So here the reference is the coherent light, which is ideal laser light. Coherent light is a superposition. That ket alpha that you see there is coherent light, and alpha can be any complex number. It's a label for the coherent state, and it's a superposition, in fact, an infinite superposition of the photon number states. So P is the P photon state and alpha is a complex number. This ket alpha, as many of you will know, satisfies the eigenvalue equation. A on ket alpha is alpha ket alpha. Now you can again have a different superposition of the photon number states and produce squeezed light, for instance. The squeezed vacuum is an infinite superposition. Like ket alpha, the squeezed vacuum is an infinite superposition of the ket p's, but with different probability amplitudes. The superposition coefficients are different. But you can also have squeezed light with a finite superposition. Example is what I've written there in blue, root 3 by 2 ket 0, where 0 is a 0 photon state and half ket 1. 1 is the 1 photon state. Now, apart from squeezed light, you can have the m photon added coherent states, alpha comma m, by simply using the creation operator, A dagger, repeatedly on the coherent light. A dagger on ket alpha, if you normalize, you will get the 1 photon added state. Go on doing A dagger to the power of m on ket alpha, normalize it, and you will get the m photon added state. In the laboratory, definitely the 1 photon added state has been identified. So again, to recapitulate, by squeezing, the reference level is set by ideal laser light. And in convenient units, if the variance the variance for laser light in the two field quadratures is equal to half. If any state of light has a spread in either field quadrature less than half, it is squeezed in that quadrature. So if light is squeezed in one quadrature, it has to be expanded in the other to respect the uncertainty principle. Now we get to the point. What is this optical tomogram? You make multiple measurements of a set of observables, which give complete information about the state. That is the quorum. What is it that I'm talking about? I'm looking at optics. So I define this operator x sub theta, which is essentially a dagger e to the I theta plus a e to the minus I theta. Now, if I set theta to 0, I get a dagger plus a by root 2, which is your x quadrature. Of course, if you're talking oscillator, it will be the position quadrature, position basis. But as I said here, I talk of field quadratures. Now, if theta is pi by 2, then I get the momentum quadrature, a minus a dagger by root 2i, that is the momentum quadrature. That's another field quadrature in the context of optics. And for various other values of theta, I get different x thetas. Now, what is the tomogram? It is the expectation value of the density matrix. Now, this is something that I measure in the laboratory. It is the expectation value of the density matrix. For a given theta, you have the state x theta comma theta. So this is the expectation value of the density matrix in that state. Now, if it's a pure state, I can always write my rho as ket psi bra psi, and it turns out to be modulus of psi squared. If theta is 0, it is modulus of psi of x the whole squared. If theta is pi by 2, it is modulus of psi tilde of p the whole squared. For other thetas, I get this. So you can see it's a probability density. And this ket x theta, theta is an eigenvector of the operator that is put up there with eigenvalue x theta. For every theta, and this is an important point, you have a complete basis x theta. The simplest way to understand it is by saying if theta is 0, I'm in the position basis. Or what is the analog of the position basis in optics? If theta is pi by 2, I'm in the momentum basis. And you can go from x to x theta by a unitary transformation. We are dealing with information. It's important to define a tomographic entropy. And as you can see, this is a takeoff from the Shannon entropy. Instead of minus p log p, you have minus integral w of x theta theta, logarithm w of x theta theta, dx theta. You see, now in terms of the tomographic entropy, I can have an entropic uncertainty relation. For every theta, the conjugate variable is at theta plus pi by 2. And this is the entropic uncertainty relation. S of theta plus S of theta plus pi by 2 is greater than or equal to log of pi. The entropic uncertainty relations have become very important, particularly in recent times. It has a very rich history, which I will not go into now. But it has become extremely important because it tells you a lot about information and laws of information. There's extensive literature on these uncertainty relations in the context of decoherence. How do you take into account the experimental losses when you formulate the entropic uncertainty relations and so on? But that is beside the point for today's talk. Before I proceed, I should give you a feel for tomograms. Now, what you see in figure A is the tomogram for the coherent state. That ket alpha, this is the tomogram. What is it that I have plotted? I have x theta on the x-axis. I have theta on the y-axis. I have plotted theta from 0 to 2 pi. That is to show the symmetry properties of the tomogram. I don't even have to do that. I can just stop with 0 to pi, because when I go from 0 to pi by 2, I go from x to p. I rotate from x to p. And then when I go from pi by 2 to pi, I come back. So I do, in the XP plane, I do a complete, circuit. And then I plot this W of X theta, theta here. This is how it looks. Look at the color code. This is how it looks for the coherent state. As I said, you can reconstruct the Wigner function from the tomogram, and the Wigner function is what is given in figure B. For the coherent state, there is no negativity in the Wigner function. For this reason, well, not this reason really, but this is one way of seeing from a very pedagogical point of view, what is classical about the coherent state. It looks like a nice probability distribution. Now, I have also put down in C, figure C, the optical tomogram for the even coherent state. So you have ket alpha, to which you add ket minus alpha. You normalize it suitably. And I have the tomogram for the even coherent state there in figure C. You can also have the odd coherent state, which is a superposition of ket alpha minus ket alpha. And you can see the tomogram for the odd coherent state. So these are some sample tomograms, just to give you a feel for how things look. Now, if you look at the Wigner functions, which I have not shown here for the even and odd coherent states, you will find that the Wigner function has some negativity in some regions of the XP plane. They are non-classical states of light. They're called cat states. Now, if you take an initial coherent state, you already know the tomogram that is there in figure A. And if you propagate it through a nonlinear atomic medium commonly modeled by something called the Kerr-Hamiltonian, which is chi a dagger squared a squared, it revives. The revival time can be seen to be pi by chi. So at revival time, you will get the same tomogram for the state as is given in figure A. Now you look at figure B. At the revival time by 4, at 1/4 the revival time, you get the tomogram given in figure B. And if you see, that has 4 strands. 2 of them are looping around and 2 are sort of standing there like the border. Now, if you look at, can you see the cursor? Yes or no?
Yes, we can.
Oh, very nice. So if you look at C, for instance, you can see that there are 3 strands. You can see 3 strands. At T-rev by 3, the tomogram has 3 strands. At T-rev by 2, and this is an easy guess, there are 2 strands. So one of the suggestions, and this is the reference by Rohit and Sudhish, Physical Review, A 2015, where they say, well, if all it is doing is propagating in a nonlinear optical medium, which can be modeled by the Kerr-Hamiltonian, you can easily look at the tomogram and find out whether it is T-rev by 4 or T-rev by 2 or what it is. So they identify fractional revivals of various orders by looking at the tomogram. But you see, life becomes a bit, let me also show you this. Now, for this same problem, if you look at T-rev, half T-rev minus epsilon, half T-rev, and half T-rev plus epsilon, where epsilon is 0.005, look at the figure caption underneath. These are the optical tomograms. See, at instant of 2 subpacket fractional revival, you see figure B on the top panel, which is definitely different from figure A, which is epsilon away from that instant, and figure C, top panel, which is epsilon away from that instant. So you can see this from the tomogram as you get to that point. So sudden changes are captured by tomograms. The Wigner function is given below. As you can see, the Wigner function looks different. The vertical Wigner function pattern is replaced by the diagonal kind of pattern in the bottom panels. So qualitative features are definitely captured in tomograms. And in the context of entanglement and so on, you can also capture quantitative features, squeezing and entanglement. Before I proceed to entanglement, I want to state that if you have cubic nonlinearity, this whole business of I will look at the tomogram and tell you whether there is a fractional revival or not is impossible because there are two time scales. See, look here. If you look at the instant t equal to 0, you have the coherent state. But then if you look at C, which is T rev by 3, where you expect to see 3 strands, you seem to come back to the coherent state. So things become murky if you have nonlinearities above the quadratic nonlinearity. Things become even worse if you have two time scales in the problem, like chi1 and chi2. Capturing features is impossible from tomogram. So I wanted to tell you the limitations of working with revivals as far as tomograms are concerned. But then you see, if you look at entanglement, life becomes different. Here I have listed a bunch of systems. One of them is, the first here is a double well Bose-Einstein condensate. The second is a multi-level atom interacting with a radiation field. The third is a cavity optomechanical system, which I put on here, where there is a two-level atom sitting inside an optical cavity and connected to a thin membrane using a spring. Then here is a workhorse of quantum optics. This is a lambda atom sitting inside a cavity, and there is going to be radiation fields mediating the 2 to 3 and the 1 to 3 transitions. And here I have put the double well James-Cummings model. There is an atom interacting with radiation field, that is the system capital A, small a. Then there is another subsystem atom capital B interacting with radiation field, small b. This is an interesting system, you know, because the radiation fields are not coupled to each other, but the atoms are initially entangled. And then Eberle has shown, this Ting Yu and Eberle, also Almeida, they've shown that you can have entanglement, sudden death and birth in these systems. It's a very interesting system. Now, in all these systems, there is entanglement. You see, there are many subsystems and they are entangled. Some of them are hybrid quantum systems. Some of them would be just two oscillators interacting with each other and so on. And you can see a variety of effects here. So how do you define the optical tomograms of bipartite systems? Same as before, extend it to two systems. I is equal to 1 and 2. So for the first system, you have your operators A and A dagger, and you define your rotated quadrature operator x theta 1. The second system, again, you have these oscillator operators B and B dagger, and you define your rotated quadrature operator x theta 2. So for a fixed theta 1, you have a complete basis x theta 1. For a fixed theta 2, you have a complete basis x theta 2. Straightforward extension of the single mode tomogram. W of x theta 1, x theta 2, theta 2. You have 4 arguments now instead of 2. The density matrix, its expectation value must be taken with respect to both these states. Now, it should be clear to you that I can generalize the concept of an optical tomogram very easily to many subsystems. For every subsystem, put in a rotated quadrature operator and talk about the grand kit. So this is, again, as I said, V.I. Manco and collaborators have done a lot of work on this. And I have given you one reference. So far, so good. Now, I mentioned the double well BEC to you. You may ask me, what is the Bose-Einstein condensate doing here? Well, I can model it with 2 oscillators. It's the same model as I would use if I have the radiation field interacting with a multi-level atom with equally spaced energy levels, which is modeled as an oscillator. These are classes of problems which can be modeled as 2 oscillators interacting with each other, or 2 radiation fields interacting with each other. These are models. So for instance, if you look at the operator A dagger A plus B dagger B, this is going to be conserved. If you use this Hamiltonian, it commutes with the Hamiltonian. Then there are terms like A dagger A minus B dagger B. In each well, the number operator is A dagger A and B dagger B. You can ask me, what are the particles in each well? Well, A dagger are the boson annihilation and creation operators here. Then you have a nonlinearity through n to the square. Then you have an interaction between the 2 wells. which is linear, like A dagger B plus AB dagger. This model works pretty nicely, and you can start with the factored product states, coherent states but now made of bosons, not photons, and see how it evolves. And you will find that under certain conditions, you will see revivals of the state. That means you started with initially separable states. They get entangled during the time evolution, but then look here. Suddenly it shows revivals. That is in D. D is a T revival. Then this is 4 subpacket fractional revivals. You can see the 4 blobs in A, and in B you see the 3 subpacket. Actually C is 2 subpackets, but they're overlapping with each other. That is thanks to the value of alpha that we have selected. The point that I'm trying to make is it doesn't have to be a coherent state of light. It can be a coherent macroscopic coherent state of bosons. And you can look for revivals here too. So this is an example, and this is the tomogram. So this is a pretty picture in the bipartite case. I want to look at entanglement. Of course, you can look at entanglement with the qubits, polarization qubit states. The superpositions are conventionally called H and V, but I'm not going to do that. I am going to look at entanglement between 2-level atoms. KG and KT are the atomic levels, and then there is light which is interacting with it. And you could start with an initial state which is unentangled. And then you will end up with an entangled state like this. Or if you're doing the Eberle model, you will start with an entangled state of atoms, but an unentangled state of the fields, and see what happens. Now you see, because there are only 2 levels here, you may send in coherent light, which is a superposition of an infinite set of states of light, basis states of light. But at a time, only 1 photon is emitted or absorbed. So you can think of, in this model, you only need 0 photons or 1 photon. And you can think of that as a qubit, you see. And if you think of that as a qubit, you can use the IBM quantum computing platform and do things. Excuse me, just a moment. Yeah, there was some disturbance. Can you hear me now? Can you hear me now?
Yes.
Okay, fine. All right.
Yes, we can.
Fine. It's pretty noisy out here. All right. So you see, the IBM quantum computing platform can be used whenever you're dealing with a finite number of 2-level atoms. You can think of, because the radiation field, only a 0 photon or a 1 photon will be used. So you can think of qubits and do calculations. In any case, now the next model, if you're looking at a radiation field interacting with a multi-level atom modeled as an oscillator with Kerr nonlinearity. Look at this. This is a subsystem linear entropy, which is 1 minus trace rho squared, where rho is the subsystem density matrix. You can choose either the atom or the radiation field. Look at this plot. As a function of time, this tells you the extent of entanglement. Now, for the state, if the initial state were, if the atom were initially at ground state, it's a multi-level atom. And if you're in a 5-photon state, look at this. The entanglement shows this interesting pattern. It is, and if you work with and the entanglement dips back in scale time, a little beyond 600, the entanglement dips back. The initial state that was used here was a factored product state, get 5, factored product, get 0. You find that the entanglement comes back to the original. It's a revival in the entanglement now. And halfway point, somewhere around 300 GT equal to 300, you see you see the analog of the 2 sub packet. And at 1/3, around 204, a little beyond 400, you see the T rev by 3 kind of thing. For the coherent state, it is somewhat worse, but A is a very nice plot. The question is, can you capture this through tomograms? And indeed you can, because this is for the upper panel is for the initial Fox state that I showed you. See, a little away, at time 625, the entanglement dips to almost 0. 1, 2, 3, 4, 5. You see 5 things there, right, in red. That is the initial 5 of the photon state, tensor product at 0. Whereas a little before and a little after, you don't see these strands. So you can capture entanglement changes very nicely in tomograms by moving a little bit away from the actual instant of drama. And in fact, even for the coherent state, you can, because I have chosen GT 1269, 1268, 1270, and you can see the qualitative changes in the tomogram. So sudden changes in entanglement can be captured very easily, but you can also quantify it. You can quantify it using things that you can calculate from the tomogram. I've already introduced to you the subsystem tomograph, the tomographic entropies. You can calculate it for each subsystem. All right. Now, if you did that, and for the full system as well. So S of theta A, theta B, A and B are the 2 subsystems. I'm talking of bipartites. So you see this P log P, you're essentially using that, realizing that your tomogram is a probability distribution. So instead of P, I use the tomogram W, the full tomogram W of X theta A, X theta B log W, and integrate over, for a given theta A and theta B, integrate over the full basis, dx theta A, dx theta B. Now, if you're talking about the subsystem tomographic entropy, you first get the reduced tomograms, which means you, suppose you want to look at subsystem A, you fix a theta B. And then you integrate over dx theta B. Whatever you get is the tomogram theta for theta A, and you can get the tomographic entropy. Now you define this object, which is the reduced tomographic entropy for subsystem A, the reduced tomographic entropy for B minus this. This is the analog of the quantum mutual information. Now this is defined for a single theta A and a single theta B, which means you're looking at tomographic slices. But as I said, one slice is not enough. Even in a medical scan, you will average over many slices. So you average over several of them in the interval theta A, theta B between 0 and pi. Normally, we have found that 25 slices are enough if you distribute it uniformly in this range. You can define an entanglement indicator, XITEI. And this one works extremely well, most times as an entanglement indicator. So as you know, mutual information has its origin in classical probability theory because it was defined in the context of continuous random variables X and Y, and it is expressed in terms of the Kullback-Leibler divergence, DKL. Now, DKL is the divergence between the joint probability distribution and the individual probability distributions. It's defined this way: the joint probability distribution, PXY, and the individual distributions, you see, Px of X, Py of Y. Now you look at this thing inside the logarithm. Now, suppose there is an entanglement. Pxy is a joint probability, but if it can be factorized as Px, Py, the content inside the log becomes 1. So things like this should tell us something about whether states are factored product states or whether they are entangled states. Because since optical tomograms are continuous probability distributions, we can now translate this idea to quantum tomograms. So you see, I'm taking elements from classical probability theory, and I'm trying to use quantum analogs to see what I can get. And that should help me understand the quantum classical divide. An alternative indicator is provided by the Bhattacharya distance. Now, that one is defined here again in terms of the joint probability Pxy and the individual probabilities Px and Py. So you see, I can define the Bhattacharya distance now using my tomograms, the 2-mode tomogram and the 2 single-mode tomograms. The same way, instead of Pxy, I use W of x theta A, x theta B. And instead of Px of x and Py of y, I use W x theta A and W x theta B. You see, wherever anything is defined in terms of probabilities in classical physics, I use tomograms. This beta BD is another very nice entanglement indicator, which I get directly from the tomograms. Now, a popular candidate which is used in defining an entanglement measure, but this one has its origins in quantum physics. This is the inverse participation ratio. It's called IPR for short. It's interesting, if you look at the history of the thing, it's interesting how much contribution chemists have made to entanglement. See, this first one, this inverse participation ratio was introduced by Bell and Dean in discussions of Faraday Society in 1970, where they were looking at atomic vibrations in vitreous silica. And they were using it in the context of quantifying the extent of spatial delocalization of atomic vibrations in a given eigenbasis of a disordered system. So in that context, they have defined the inverse participation ratio. Then subsequently, because this entanglement business became big matter, using this inverse participation ratio, entanglement measures have been defined. And they will involve mod psi to the 4, basically. The reason is simple. As you could have seen from my earlier discussions, you need the bipartite tomogram. You need x theta A, x theta B, which means it's like looking at rho squared. And rho is ket psi bra psi. So it is looking at mod psi to the 4. So the IPR would, the entanglement measure based on the inverse participation ratio will involve mod psi to the 4. Subsequently, chemists have really worked on this, and they use a lot of indicators based on the inverse participation ratio, but this too can be calculated from the tomogram. And so, as I said, from the tomogram, IPR can be got. See, this is the tomogram, the two-mode tomogram whole squared. So it is like mod psi to the 4. And you integrate over dx theta A and dx theta B. You also need the subsystem tomograms, and you define an entanglement indicator, epsilon IPR, which is 1 minus, add the subsystem values eta A and eta B, and from them subtract eta AB. So if once more you're doing it for a tomographic slice, given by theta A and theta B fixed values, this dependence is removed by taking an average over the core. I hope you have got a feel for how to work with tomograms. If you want entanglement, you first work with the two-mode tomogram and then with the reduced tomograms and define quantities which are combinations of these. Here is a nice example. This is xi IPR, the average value. This is you in the lambda atom interacting with two fields, which I mentioned earlier. You trace out the atom. Look at the mixed state of the two field subsystems. The entanglement between the two field subsystems is given by xi IPR, and you see the way it takes dips. For plot A, tau is equal to 0 to 150. It has been, tau is a scale time. And you can see the way it takes dips around 55 and somewhere around 125. Then again, at somewhere between 2200 and 2300. The quantum information, quantum mutual information versus tau, if you plot for the system, it is similar to xi IPR. So we have tomographic entanglement indicators, which mimic the known standard measures. See what I told you earlier. So for one of the fields, if you look at scale time 55, 60, 65, look at the dramatic change in the appearance of the tomogram. This is where the entanglement took a big dip. Similarly, for larger times, 2200, 2250, 2300, in the bottom panel, look at the changes in the appearance of the tomogram. So the qualitative feature will change dramatically when there is a terrific entanglement change. So you can read off many things from tomograms. In fact, you can, as far as squeezing properties are concerned, variances can be calculated very easily from tomograms and also the higher moments. So the extent of squeezing as a function of time, the way it changes, can be quantified very well from tomograms. Qualitative changes in entanglement can be easily captured from tomograms. They can be quantified using tomographic entanglement indicators. Synchronization. People talk a lot about synchronization, quantum synchronization these days. Now, synchronization between quadrature operators in the Lambda system, we have used a synchronization measure defined this way. You define the difference between the quadrature operators of the two radiation fields, P1 and P2, and similarly Q1 and Q2. These are like the X and the P quadratures. And we call them Q minus and P minus, look at their variances and define a quantity SC. And if they are synchronized, this SC should go to 0. And you can see that, this SC versus tau, if you compute, it goes to 0 in the initial stages itself. This has been plotted for scale time 0 to 5,000 and on a shorter scale 0 to 100. You see at 5, it goes to 0. Look at the tomograms, the bottom panel. It started with an initial coherent state, factored product coherent states for the fields. Look at it. Look at the very next top panel, which is dramatically different from the initial coherent state and from the tomograms that follow later. If you look at the Wigner function again, you can capture it in the Wigner function too, as you can see, but you don't need to reconstruct. I can see this from the tomogram itself. So quantum synchronization is again the instant of synchronization can be captured very readily from the tomograms. State reconstruction can be completely avoided in all these contexts. Tomograms can also be chronocyclic tomograms. That means omega and time, frequency time. You can use frequency and time as your conjugate variables. And in fact, we have worked with an experimental paper where they had 2 frequency combs. Each of them was entangled 2 photon states. So the first one was an entangled 2 photon state. The second was an entangled 2 photon state. The question asked is, how do you see the difference between these two? Of course, in the experiment, they did interferometry. They looked for Hongu-Mandel effect. They looked for the famous Hongu-Mandel dip and so on. You don't need all that. Look at the tomograms. So one of the biphoton frequency combs looks like this. The other one looks like that. That's all. I can rest my case right here because I don't need to do the experiment in full measure. All I need are the 2 tomograms. But these are frequency time. So as you can see, you can have optical tomograms, you can have spin tomograms, and in optical tomograms, you can have quadrature tomograms like XP that I spoke about, or the frequency time tomograms that I have given you here, and so on, and read off many things from the tomogram. So let me summarize. Qualitative features of optical tomograms suffice to capture occurrence of revivals, fractional revivals, changes in entanglement, onset of synchronization, and other non-classical effects. Now, quantification of entanglement using the tomographic indicators seems reliable and applicable. You can use the same procedures for examining classical entanglement, synchronization, and so on. What is the ultimate aim? 2 things, actually. Because we are using probability distributions and not quasi-probability distributions in our approach, you can see, this is one way of seeing the quantum classical divide, where exactly quantum mechanics takes off. The other thing is, I don't see much else option. Reconstructing a state is not an easy matter if you have a multipartite system. Might as well read off a lot of things from tomograms. So they come up as, they come up looking very good. Tomography looks very good. So I'd like to stop here and take questions.
Yeah, thank you, Dr. Bala. Now, some questions are already in the chat box.
I can't see the chat box.
Maybe
unless I stop sharing screen.
Yeah, so people, you can unmute yourself and ask. There's one question in the BEC model work for many body systems. No, there is something about BEC. I'm not very clear about that.
Okay, let me see. Maybe if I stop sharing, I can see the chat.
Yeah, I think you can do that.
Shall I stop sharing? I'll stop sharing first. Yeah. Then I can see the chat box.
Yeah.
Okay, so I don't understand. Okay. Where do I start the questions?
You can start, that what is.
In other words, characterization of entanglement and so on. No, where does my part begin? There is a whole lot of yes ma'ams going.
You can start with, that last question, which is what is a quantum?
The last question.
Quantum.
What is quantum mutual information? What does this indicate? All right. The quantum mutual information, loosely speaking, yes, it indicates quantum correlations. No, it does not indicate correlations beyond entanglement. But it tells you how much information is shared between two parties. And that is why in the earlier talk, Professor Singh also told you, if there is an Alice and a Bob and an Eve, and if the information shared between Alice and Bob is more than the information shared between Alice and Eve, for instance, where Eve is the eavesdropper, the mutual information will be more between Alice and Bob than between Alice and Eve. So the information shared, loosely speaking, that is what it is. Okay.
Yeah,
is this BEC model work for?
Yeah. So I have a related question here, Lakshmi Bala. See, in this Bhattacharya distance, you replace the probability distribution by Wigner function. Is that right? By
tomogram. That W for me is always tomogram.
Okay, so that W, if it becomes negative, you have a square root there, no?
No, W is the Wigner function becomes negative. I think there is a confusion in the notation. I don't use Wigner functions at all.
Okay.
For me, W is tomogram, and the tomogram never becomes negative. So P log P, wherever there is a P, I use the tomogram.
Okay.
So P of P sub XY is my two-mode tomogram. P sub X is my reduced single-mode tomogram. And everything is non-negative. The next question, is this BEC model work for many body systems, many quantum atoms? See, look, it is like this. You can write a model of oscillators interacting if there are many bodies, provided they are equally spaced, and you can treat them like bosonic oscillators and write the model. But what I am looking about is bipartite entanglement, not multipartite entanglement. So that means if you have 5 such subsystems, I'm going to take 4 of them as one subsystem and the other as the other subsystem, and look at entanglement between the single guy and the remaining 4. So what I have given you are the bipartite indicators, not the multipartite indicators. But yes, you can write a model. That's not the issue. More important question is, can you give me an indicator from tomograms for multipartite entanglement? At the moment, I cannot. And we are working on it. Then there's a whole lot of yes going. Yes, what is the experimental application of entanglement revivals? See, more than experimental application, people like entanglement. I mean, the entanglement is a good resource. In all my models, you will find that I started with 0 entanglement. I started with a factored product state. So if it gets back to the unentangled state, that's not a very happy situation. So you would like to see the time intervals over which entanglement is non-zero and where the dip is not there. Then yes, in the Lambda system that I spoke about, the entanglement actually collapses to a constant non-zero value over a significant period of time. That's very good. That's very good news, because it gives you a sufficient time interval where you can use entanglement as a resource. If it collapses to 0, there is a problem. If it doesn't collapse, it's going on changing. What do you do with it? It's good to identify time intervals, substantial time intervals, where it collapses to a constant non-zero value. That is available in the Lambda system under certain conditions. So then it can be used as a resource for quantum information processing. Okay, for entangles.
Hi, very good afternoon.
Afternoon, yes.
Ma'am, I just
Oh, I
want
should
to
say very good afternoon. Okay. So,
thank you. Ma'am, what I wanted to ask is, are there any examples of what you have explained over the last hour in biological systems?
Chronocyclic tomograms, yes, because people have looked at biological systems to see how things are entangled. And they have looked at entanglement indicators in that context. Now, what is the impact for biology? I do not know. How exactly they will use it they've seen it in photosynthesis. But how useful it is, do you need this at all? I do not know. But medical scan is a tomogram. So certainly in medicine, it is the most useful thing possible. It is the first thing that you will do. Photosynthesis, yes, they have used entanglement measures with chronocyclic tomograms, but I don't know the impact.
I apologize, ma'am. Was that chronocyclic or chromocyclic?
Chronocyclic.
Time, okay. All right.
Yeah, chronology, frequency, time. Yeah.
Thank you very much, ma'am.
Welcome.
There are some questions in the chat box.
Yeah, I'm seeing. For entangled state, due to atomic transition, the field qubit has 0 photons and 1 photon. But for what kind of atomic transition? Well, it depends. Suppose you're looking at a 2-level atom, there are exactly 2 levels. Then you absorb 1 photon. You kind of see to it that the input light you see to it that the resonance condition is matched. That means that the H cross omega for the input light is the same as the H cross omega for the atomic transition. If it's close to resonance, the probability of transition between these 2 levels is high, and then it absorbs either 1 photon or 0 photons. So you can think of it as qubit. You may have more than 2 levels also. The question is, if the drama is between 2 levels, and if the resonance condition is taken care of, then you can always model it. Doesn't matter what these 2 levels are, even in a multi-level atom. You can model it as 0 and 1. If you can identify such 2-level atoms, and if you have an array of them, you can translate this whole thing into an IBM quantum platform. And I thought students are very good at playing with the IBM quantum platform. So it's a good thing to do. Is there any application of quantum tomography in high energy physics? I've seen papers on quantum correlations in neutrino oscillations, or in another way, can we apply the steps written for bosonic Hamiltonian to systems of fermions via some transformation? No, let me answer this question carefully. I myself started off with high energy physics for my career, and therefore I think I've been keeping in touch with this jet tomography. Jet physics uses a lot of tomography. What are these jets? You see, for instance, if you collide electrons with positrons and you get hadrons, these hadrons come out as jets in the final state. A jet is a cone, you know. There is an apex and then it comes out like a cone. And you want to identify the particles in this jet. The problem arises because you use the quark model to describe this, but you don't see free quarks because of quark confinement. And what you see are the protons or whatever hadron comes out. So you look at the tomograms for the jets, and then you avoid reconstruction of the hadrons using parton distribution functions and so on, but you try to infer from the jet tomogram what are the particles that come out. So yes, indeed, tomography is big matter. It's big matter from medicine to high energy physics. So that's the answer to the first part. Then, can we apply the steps written for bosonic Hamiltonian to systems of fermion via some transformation? Not via some transformation. You're basically working with 2 levels. So you can think of spin tomograms or qubit tomograms and apply them to fermions. That is possible. There have been some papers on it, though I have not followed it up. Does entropic uncertainty relation help in description or characterization of entanglement? Yes, indeed. I have not explained that part to you. Whenever there are sudden changes in entanglement, you will find that the entropic sum, that S of theta plus S of theta plus pi by 2 jumps up or goes down. So yes, it does help you understand sudden changes in entanglement. That is one thing that it does. Then there is a, I don't see, I see a thank you, ma'am. So I think we can start.
Okay, so thanks, Lakshmi Bala, very nice, and we all got updated about your research works, recent ones. Very nice.
Thank
Fits
you.
into the theme perfectly. Morning session.
Thank
So thank you once again.
Thank you very much.
And
Welcome.
our participants will meet at 3 o'clock. Solomon, Dr.
Oh,
Solomon
somebody
Bala.
has raised his hand. 1 minute, 1 minute.
I think
Deborishi
Deborishi
Ganguly
probably
raised
has
hand.
not put it hand down because he asked the question.
Oh, he hasn't put his hand down. Now he has put his hand down, so we can all leave. Oh, okay.
So sorry, ma'am.
No problem.
Okay, no problem, no problem. Yeah. Okay, then.
have a
Thank
good
you so
lunch.
much. Wish you all the best with your conference. Bye.
Thank you.